Have you ever looked closely at a train wheel and noticed something odd? The surface isn't flat. It's slightly angled, almost cone-shaped. The edge has a raised lip that seems unnecessary. And the whole design looks nothing like a car tire or truck wheel. Why would engineers create such a strange shape? What problem does it solve? And how does this geometry keep thousands of tons of steel on the rails? In this video, we'll break down that engineering mystery piece by piece. At first glance, a train wheel seems overcomplicated. A simple cylinder would be easier to manufacture and cheaper to produce. But in reality, this shape performs one of the most critical tasks in rail transportation. It keeps the train centered on the track without any steering input from the driver. In the early days of rail transport, engineers experimented with various wheel designs. Flat cylindrical wheels were tested first. They rolled smoothly and seemed adequate for straight sections of track. But there was a fatal problem. On curves, the train would derail constantly. The wheels had no way to navigate turns. They would either climb off the rail or grind against it until the friction became unbearable. Something had to change. For a long time, the solution seemed obvious. Add a flange, a raised lip on the inner edge of the wheel that would prevent it from sliding off the rail. And flanges were added. But engineers quickly discovered that relying solely on the flange created new problems. Every time the train entered a curve, the flange would slam against the inside of the rail, causing violent impacts, excessive wear, and uncomfortable jerking for passengers. The breakthrough came when someone realized the wheel itself could steer the train. Not through moving parts or complex mechanisms, but through pure geometry. The secret is in the taper. Train wheels are not cylindrical. They're slightly conical, with the diameter gradually increasing from the outer edge toward the flange. This taper is usually just a few millimeters across the width of the wheel, but that small angle changes everything. When a train enters a curve, centrifugal force pushes the entire wheel set slightly to one side. As the wheel set shifts laterally by just a few millimeters, the wheels begin rolling on different diameters. The outer wheel in the curve rolls on a larger diameter section. The inner wheel rolls on a smaller diameter section. Because both wheels are fixed to the same axle and must rotate at the same speed, the wheel with the larger diameter travels farther with each revolution. This creates a difference in the distance covered by each wheel, allowing the wheel set to naturally follow the curve without the flange ever touching the rail. This is not random. It is a self-correcting mechanism built entirely into the wheel's shape. If the train drifts too far to one side, the geometry automatically brings it back toward the center. The wheel set oscillates gently from side to side as it rolls, always seeking the balanced position where both wheels are rolling on equal diameters. This continuous self-adjustment keeps the train on track through curves, switches, and imperfections in the rail alignment. No steering wheel, no electronic guidance, just physics and geometry working together. But the flange is still there, and it still has a purpose. The flange is not the primary steering mechanism. It is the safety backup. In normal operation, the flange should never touch the rail. It hovers just millimeters away, waiting. If the train encounters a sharp curve, a sudden track misalignment, or excessive lateral forces, the flange engages and prevents derailment. Without it, even the conical shape would not be enough to keep the train on the rails under extreme conditions. The flange is the last line of defense, and its presence allows trains to operate safely at high speeds, even on imperfect track. Another critical factor is differential rolling. On a car, the left and right wheels are mounted on separate axles, connected through a differential gear system. This allows each wheel to rotate at a different speed during turns. Trains do not have differentials, Both wheels on an axle are rigidly fixed together and must rotate as one unit. This creates a challenge. During a curve, the outer rail is longer than the inner rail. The difference can be substantial. On a curve with a radius of 500 meters and a standard gauge of 1.435 meters, the outer rail can be several centimeters longer than the inner rail over just a short section of track. If both wheels were the same diameter, one would have to slip or skid to compensate. But because of the conical taper, the wheels effectively change diameter as they shift laterally on the rail. This differential rolling eliminates the need for a mechanical differential and reduces friction dramatically. The energy that would otherwise be lost to sliding friction is conserved. The train rolls smoothly through curves with minimal energy loss and significantly reduced wear on both wheels and rails. Track gauge, the distance between the two rails, is not perfectly constant. Manufacturing tolerances, thermal expansion, and track settling cause slight variations. A train wheel must accommodate these changes without losing stability. The conical shape provides that flexibility. When the gauge widens slightly, the wheel set shifts outward and rolls on a smaller diameter section of each wheel. When the gauge narrows, the wheel set shifts inward and rolls on a larger diameter section. This self-adjusting behavior absorbs variations in track geometry and prevents the wheel from binding or derailing completely. Over time, train wheels wear down. The contact patch where the wheel meets the rail experiences immense pressure, often exceeding several tons per square centimeter. At the point of contact, temperatures can rise significantly due to friction, sometimes reaching several hundred degrees Celsius during heavy braking. Metal fatigue, friction, and constant loading create wear patterns on the wheel surface. The conical taper gradually flattens. The flange thins. Hollow wear can develop on the tread surface, creating irregular contact with the rail. If left unchecked, this wear degrades the wheel's ability to self-steer and increases derailment risk. That is why train wheels are regularly inspected and reprofiled using specialized wheel lathes. These machines grind the wheel surface back to its original conical shape, restoring the precise geometry required for safe operation. The process can remove several millimeters of material in a single session, carefully recreating the exact taper angle specified by the manufacturer. This reconditioning can be repeated multiple times over the wheel's lifespan, with some wheels being reprofiled 10 or more times before replacement becomes necessary. The forces acting on train wheels are extraordinary. A fully loaded freight train can weigh over 10,000 tons. That weight is distributed across dozens of wheel sets, but each individual wheel still carries tremendous load. During acceleration, braking, and cornering, these forces multiply. At high speeds, additional dynamic forces come into play. Vibrations from track irregularities, centrifugal forces in curves, and aerodynamic effects all add stress to the wheel structure. The wheel must absorb these forces without deforming or cracking. The conical profile is not just about steering. It also distributes load more evenly across the contact patch, reducing stress concentrations that could lead to metal fatigue and eventual failure. High-speed trains traveling at 300 kilometers per hour or more place even greater demands on wheel geometry. At these velocities, even minor imperfections can cause instability or excessive vibration that threatens passenger comfort and safety. Modern train wheels are made from high-strength steel alloys specifically engineered to withstand extreme mechanical stress and thermal cycling. The material must be hard enough to resist wear, but tough enough to absorb impacts without cracking. Heat treatment processes, including quenching and tempering, are used to optimize these properties. The result is a wheel that can endure millions of kilometers of travel while maintaining its geometric integrity. Some high-speed trains use wheels with advanced coatings or composite materials to reduce friction and improve performance. But the fundamental conical shape remains unchanged. A train wheel is far more than just a simple rolling component. It represents a brilliant and elegant solution to a complex mechanical problem. The conical taper, the flange, and the rigid axle work together seamlessly to create a self-steering system that has remained fundamentally unchanged for over a century. And if you would like to learn how other types of railway technology work, let us know in the comments.